In this lecture, we will discuss a very important class of functions called Mobius transformations. Mobius transformations are special rational functions which naturally occur in the study of various domains in complex analysis. But before we get into the study of Mobius transformations, it will be useful to study the extended complex plane. The extended complex plane is nothing but the complex plane with one point attached to it. If you have seen our course on topology, it's just the one point compactification of the complex plane. Let me begin by defining what an extended complex plane is, and we will give a concrete description of what that is. So, the extended complex plane. We define the extended complex plane and denote it by C hat. To be the set C hat, which is given by C union the point at infinity. The extended complex plane is very important, especially in the study of a class of functions which diverge away to infinity at isolated points. They are the right setting to study such functions, and we can give a concrete description of the extended complex plane by looking at the sphere in R3. So, recall that the sphere in R3 is given by just the higher dimensional log of the unit circle. This is the set of all, so let's denote it by S2. This is the set of all x1, x2, x3, such that x1 square plus x2 square plus x3 square is equal to 1. This is the equator, which is at the back, and let me just identify this with the xy plane here. So, this is the xy plane and any point here. So, this xy plane can be identified with the complex plane, and this is the unit sphere with the origin here. Let's get hold of a distinguished point. Let's call this point P, which is the point 0, 0, 1, which is at the top of the unit sphere. And for a given point Z in the complex plane, let me use another color. Let's join this point Z with the point P. And the point will, so given Z here, there is a point phi of Z on the unit sphere. So, let's see, let's capture all that we just said. Let Z be equal to xy0 be a point on the xy plane or the complex plane. Be a point, let me just write for simplicity a point in C. It's the complex plane is being identified over there. As of now, I am just considering this as a set, and what is going to be a line which joins Z and P? Then the line joining Z and P is given by 1 minus t times Z plus t times P, where t belongs to all real numbers. This is the line which joins Z and P, and the thing we are interested in is the point at which this line meets the unit sphere, and that's given by a very simple equation, which is basically the following. It's going to be 1 minus t so this is in coordinates, this is going to be 1 minus t times x, 1 minus t times y, and t times 1, which is This is going to be the set of all points. This L is going to be the set of all points where T is in R. We are interested in the point where it touches our unit sphere. It is given by this equation: x1 square plus x2 square plus x3 square is equal to 1, which can be written more compactly in this manner: plus t square is equal to 1 minus t square. Of course, when t is equal to 1, we are at the point P, and we are not interested in that. Well, hence for t not equal to 1, we have mod z square is equal to 1 plus t by 1 minus t, and you can get hold of t from here, which gives t is equal to mod z square minus 1 by mod z square plus 1. So this is precisely the point, the parameter t at which it touches the unit sphere. So hence L meets S2 at 1 minus t times x, which is going to be 2 times x by mod z square plus 1, 2 times y by mod z square plus 1, and mod z square minus 1 by mod z square plus 1. So this is precisely the point where it touches the unit sphere. So let's define a map. At this, define a map phi from C into S2 given by phi of z is equal to 2 times real part of z by mod z square plus 1, 2 times the imaginary part of z by mod z square plus 1, and mod z square minus 1 by mod z square plus 1. If you notice, this map takes every point outside the unit circle onto the upper hemisphere. Any point inside is taken into the, any point here will be mapped. This is the point, say z prime. The map p of z prime will be on the lower hemisphere, and any point on the unit circle will be mapped to the same point. You can actually construct the explicit inverse and see that phi is going to be an injective map from C to S2, or rather, let me define the map by defining phi of infinity to be equal to P. We have a bijection from C hat, which is the extended complex plane, which is the set C with the extra point infinity attached. This is a bijection from C hat to S2. This is a concrete description of the extended complex plane. This map phi has a name. It's called the stereographic projection. The identification is quite important. Phi is called the stereographic projection. Using the stereographic projection, we will also define a metric on C hat. Given 2 points z and z prime in C hat, we will define the distance, stereographic distance from z to z prime to be the Euclidean distance from phi of z to phi of z prime. Remember that phi of z and phi of z prime are 2 points in R3 which lie on the unit circle or unit sphere. We will define the stereographic distance from z to z prime to be exactly the Euclidean distance of phi of z to phi of z prime. Let me not spend too much time deriving the expression. I'll just write down the expression for you. We define a distance on C hat as follows. Distance d of z comma z prime is equal to the distance of p of z to p of z prime in S2, which is contained in R3. So this distance is the Euclidean distance. Let me just write it here. And the explicit expression is just going to be the following. This is going to be equal to mod of z minus z prime by 1 plus mod z square into 1 plus mod z prime square to the power 1 by 2. Now this is the case when both z and z prime are not infinity, the point at infinity. If one of them is, say, the point at infinity, then d of z prime is just going to be equal to, oh, I missed a 2 here. So the d of z prime is just going to be equal to 2 by 1 plus mod z square. So notice that with respect to this metric, the neighborhoods of the point at infinity will just turn out to be the complement of balls in the complex plane. So that's the topology you get on the one-point compactification, right? The neighborhood around infinity is going to be the same. So this is a good description to keep in mind of the extended complex plane. So we are now in a setting to define what Mobius transformations are. Mobius transformations, as I had said earlier, are special class of functions which naturally occur at various stages in complex analysis. The definition is quite straightforward. A map S of z given by az plus b by cz plus d. So it is the fraction of two linear polynomials. Such a map is called, so for a, b, c, d complex numbers, such a map is called a Mobius transformation if AD minus BC is not equal to 0. Let's look at a few examples. The identity map is the first example of a Mobius transformation. Is a Mobius transformation. In this case, A is equal to 1, D is equal to 1, B and C are 0. Okay, another example would be the map S of Z given by Z minus I by Z plus I. In this case, B is minus 1, A, C and B is minus I, and A and C are 1, D is equal to I. So notice that S of Z in the second case here, it's holomorphic away from minus I. Because it's a rational function, the function is holomorphic away from the zeros of the denominator. So maybe on a more general note, Mobius transformation is holomorphic. Mobius transformation, specifically say S of Z equal to AZ plus B by CZ plus D, is holomorphic at points at C minus of D by C. The singleton minus of D by C, which is the 0 of Cz plus D, is precisely the point which is to be thrown out. Everywhere else, our given function is going to be holomorphic by the quotient rule. So that's one observation to keep in mind. So consider now the following Mobius transformation. Consider as maybe T of Z given by dz minus b by minus of cz plus a. Such a map is going to satisfy the following condition. At points where it makes sense, we can say that T composed with S is going to be equal to identity. So this is going to be defined where it is going to be defined at the points where Z is not equal to minus of D by A, because that's the expression here, that's the place where it is defined. And one more point has to be thrown out, which is the pre-image of my A by C. So these are the 2 points where we will have to worry about, but we'll come to that in a minute. The idea is that the first thing to note is that Mobius transformations can be composed. We'll get back another Mobius transformation. So another observation, observe that Mobius transformations, wherever it can be composed to obtain another Mobius transformation. So from a very abstract group theoretic point of view, we are in a good setup. The Mobius transformations, they form a group. We in fact explicitly gave what would be an inverse of a given Mobius transformation. Mobius transformations form a group. But then we were worrying about the points minus of D by A and the point where the denominator of S inverse vanishes. So in order to get ourselves in a better situation, let's define the map S as a map on the extended complex plane rather than on the complex plane. We shall consider a Mobius transformation to be defined on C hat rather than on C by defining, we were having one point left out, right? For S of Z equal to AZ plus B by CZ plus D, S of minus of D by C, we will define it to be the point at infinity, which we have attached to the extended to the complex plane to obtain the extended complex plane. So notice that this infinity, the symbol infinity, is being used because in some sense it coincides with our notion of infinity, which we have developed in a real analysis course. So here minus of D by C is now going to be sent to the point at infinity, and where will the point at infinity be sent to? It should be sent to the point where we will have a singularity for S inverse. So the point here would be at A by C. S infinity is going to be defined to be A by C. Then it's a good exercise for you to sit down and check. S is a bijection. We have already done all the hard work. I have in fact given you an explicit inverse on C hat. So it's a map from C hat to C hat, which is a bijection. Okay, let's look at a few more examples. A very important group of Mobius transformations are the translations. So another very important Mobius transformation is the translation. S of Z is given by Z plus B for B in C. Such translations, such Mobius transformations are called translations. Another group of Mobius transformations of great interest is dilations. S of Z is equal to A times Z for A not equal to 0. How about the third one? Third one is the inversion. So notice that dilations are, examples of dilations are things which we have already considered. For A equal to elements of the type e to the power I theta, we have already seen that S will turn out to be isometries of the complex plane which fixes the origin, right? We have already seen that. So basically a rotation, they will turn out to be rotations. Dilations are more general. For any a not equal to 0, we can talk about S of z is equal to az. That's going to be a Mobius transformation, by the way. And the third one, which is of interest, is the inversion rather, S of z given by 1 by z. So notice that when we are looking at Mobius transformations of the type az plus b by cz plus d, if c is equal to 0, then the denominator doesn't have a root, and in such a scenario S infinity is defined to be infinity itself. So this is something which should be kept in mind. When c is equal to 0, then S of infinity is equal to infinity, and that's how we will extend it in that case to the map on the complex plane, extended complex plane. Right, so we have seen a few examples here, and these examples were not picked arbitrarily. The following proposition tells us that these examples are very special in the sense that every Mobius transformation can be written as a composition of a rotation, a translation, and an inversion. Not necessarily all of them appearing in the composition. Nevertheless, any Mobius transformation can be written in this manner. Let me write down the statement for you. Any Mobius transformation can be written as a composition of translations, dilations. Rotations are just a very special subcategory of dilations. Dilations and inversion. Not all of them necessarily appearing. For example, if you take a dilation, it's already a dilation. We don't need a translation and inversion now to get it as a composition of these. So that's the statement of the proposition. Let's give a proof. The proof is quite straightforward. It's just getting hold of the right translations and dilations to describe our Mobius transformation. Suppose our S of z is of the type az plus b by cz plus d. Two cases can happen. If c is equal to 0, then our S of z is going to be, we could have just considered az plus b, but let's anyway stick to what we have just taken. This is going to be a by d times z plus b by d, and this is going to be equal to S1 composed with S2 of z, where S2 of z is first the dilation by a by d, and S1 of z is a translation. That's translation by b by d. So if you notice, we have a dilation and a translation whose composition will give us our given Mobius transformation when c is equal to 0. The more difficult case, or rather more complicated case, is when c is not equal to 0. In the case when c is not equal to 0, we will need more Mobius transformations, more of these elementary Mobius transformations. So if c is not equal to 0, I'll just leave it to you to check that. Let me just write that in bracket. Check that S is equal to S4 composed with S3 composed with S2 composed with S1, where S1 of Z is translation, S2 of Z is the inversion, S3 of Z is a dilation of the type BC minus AD by C square times Z, and finally S4 of Z is another translation. So if you sit down and do the computations, you will see that S4 composed with S3 composed with S2 composed with S1 will turn out to be our given Mobius transform. How we can write a given Mobius transformation as a composition of translations, dilations and inversion. Let's try to understand Mobius transformations a bit better. And in order to do that, it's quite useful to look into the fixed points of our given Mobius transformation. So that will be our next goal, studying the fixed points of given Mobius transformation and concluding things from that. So let's start with Mobius transformation. Let S of Z be equal to AZ plus B by CZ plus D. Let's look at a few of the examples we had considered before we actually do this. The first one was the identity map. The identity map had the property that every point is a fixed point. But let's look at the translation. The translation here. What will be a fixed point of this translation? Z plus B being equal to Z is what matters. For B not equal to 0, when B is equal to 0, it's again the identity map. When B is not equal to 0, Z plus B is not equal to Z for any of the points on the complex plane. However, the point at infinity is a fixed point. Okay, how about S of Z is equal to AZ? Now, if A is equal to 1, this is the identity map. When A is not equal to 1, this is going to be Z is going to be a fixed point if Z is equal to 0. And we also know that the point at infinity is a fixed point here. So in this case, the fixed points will turn out to be 0 and the point at infinity. And how about here? Here, Z will turn out to be equal to 1 by Z, which implies that Z is equal to plus or minus 1. In any case, in all these cases, we will notice that we are ending up with a quadratic polynomial, and that's going to be the case with a general Mobius transformation as well. So let S of Z be equal to AZ plus B by CZ plus D, then Z is a fixed point, implies that AZ plus B is equal to Z times CZ plus D, and we end up with a quadratic polynomial of the type C times Z square plus D minus A times Z minus B is equal to 0. And we know that such a polynomial will have a maximum of 2 distinct roots. Hence, if S is not the identity, then S can have a maximum of 2 fixed points. So in particular, if S has 3 fixed points, it's supposed to be the identity map. So there are a few special cases which one has to consider here when C is equal to 0, when D is equal to A is equal to 1. But let me leave it to you to sit down and check. In all these cases, it turns out that by considering the map explicitly, by looking at, for example, when C is equal to 0, the map is just going to be equal to A by D times Z plus B by D. And in that case, we know exactly what the fixed point will be. One point will certainly be the point at infinity, and the second point can be obtained by looking at A by D times Z plus B by D is equal to Z and solving for it. There will be a linear equation, and therefore there will be one root. So there will be a maximum of 2 fixed points. So the cases where these things vanish is of interest. When C is equal to 0 and D is equal to A, again you should go back to how S of Z looks like. This is going to again get satisfied. The fact that S can have a maximum of 2 fixed points. This observation has far-reaching implications, because if you take 3 points A, B, C, so let A, B, C be distinct points, and alpha, beta and gamma be such that S of A is equal to alpha, S of B is equal to beta and S of C is equal to gamma. Let's now take some other Mobius transformation which does exactly the same. Let T be another Mobius transformation such that T of A is equal to alpha, T of B is equal to beta and T of C is equal to gamma. Then what do we know about T inverse composed with S? We know that this is a Mobius transformation because composition of Mobius. T inverse is a Mobius transformation. We know the explicit formula once we know what T is. And then T inverse composed with S is also going to be a Mobius transformation. So T inverse of S is a Mobius transformation which does a little more than ordinary. It fixes three distinct points A, B, C in the complex plane, actually in C hat. So I could have taken three distinct points in C hat. So this tells us that the action of a Mobius transformation on 3 points completely tells us what that Mobius transformation is. There cannot be another Mobius transformation which acts similarly on 3 distinct points. So we can now ask, given 3 distinct points, can we get hold of some nice Mobius transformations which map it to points of interest to us? And the answer is yes. We will now try to construct Mobius transformations which map 3 given distinct points A, B, C to the points 0, 1 and infinity in C hat. Let's do that. Let A, B, C be points in C hat be distinct. Then the following cases happen. If A, B, C belong to C, none of these points are the point at infinity. Let's define S of Z to be equal to Z minus A, which will send the point to point A to 0. Now this is going to send the point B to 1, and this is going to send the point C to infinity, and which now is maintaining the fact that B is sent to 1. So if you define S of Z to be this, notice that B minus A and B minus C are complex numbers. By multiplying it by the complex number, you are going to get hold of a Mobius transformation here. Check that, then S of A is equal to 0, S of B is equal to 1 and S of C is equal to infinity. So we can explicitly get hold of a Mobius transformation which maps these 3 points to 0, 1 and infinity. This can be arranged when one of them is infinity as well. So if A is equal to infinity, and let's see what happens. Then define our S of Z in the following manner. We want A to be sent to infinity, C should be sent to, A should be sent to 0, C should be sent to infinity and B should be sent to 1. So check that this particular Mobius transformation satisfies all our requirements. Satisfies S of infinity is 0, S of B is equal to 1 and S of C is the point at infinity. Now next is the case when B is infinity. There it's quite straightforward because B is going to get mapped to 1. This is just going to be Z minus A by Z minus C. So notice that C is getting mapped to infinity here, A is getting mapped to 0 and B, which is the point at infinity, is getting mapped to 1. And finally, if C is the point at infinity, what will be the case here? We want infinity to be mapped to infinity, right? And that's just going to be the case when it's going to be a linear polynomial. There is nothing in the quotient. The quotient is going to be a constant. And what more do we want? We want A to be mapped to 0 and B to be mapped to 1. So this is precisely going to be the Mobius transformation which does the trick. So let me write down a proposition which we have just proven. Given distinct points A, B, C in C hat, their x is unique, that we have already shown, unique Mobius transformation such that S of A is equal to 0, S of B is equal to 1 and S of C is equal to infinity. We have taken care of all the possibilities as well, right? A, B or C, one of the three could be, they are distinct points. One of the three could be infinity, the point at infinity, and still we have got hold of Mobius transformation which manages this. We have proved this proposition. In fact, we have proved a little more. We have proved the following corollary. Given distinct points A, B, C in C hat and distinct points alpha, beta and gamma in C hat, there exists a unique Mobius transformation which maps A to alpha, B to gamma and B to beta and C to gamma, such that, there exists a unique Mobius transformation such that S of A is equal to alpha, S of B is equal to beta and S of C is equal to gamma. The proof here is quite straightforward because we have explicitly constructed Mobius transformations which can map A, B, C to 0, 1 and infinity in that order, and similarly alpha, beta, gamma to 0, 1 and infinity in that order. We just compose S1 and S2 inverse. Just write that down, whatever I just said. Let S1 be Mobius transformation such that S1 of A is equal to 0, S1 of B is equal to 1 and S1 of C is equal to the point at infinity. Similarly, we know the existence of one such S1 from the previous proposition. Similarly, S2 be Mobius transformation such that S2 of alpha is equal to 0, S2 of beta is equal to 1 and S2 of gamma is equal to infinity. Then S2 inverse composed with S1 T defined in this manner maps A, B, C to respectively alpha, beta, gamma, and we are done. So not only do we know that action on A, B, C will determine the Mobius transformation, but we also know that given A, B, C and alpha, beta, gamma, we have a Mobius transformation which maps A to alpha, B to beta and C to gamma. Let's conclude this lecture by proving a very nice property of Mobius transformation, namely that it maps circles to circles. So when I say circles here, I mean the generalized circle. So let me rephrase it. Mobius transformations are special in the sense that they map generalized circles to generalized circles. Generalized circles are the circles which could either represent the circle or the straight line. It was already discussed in one of the problem sessions. Let me just recall it for you. Nevertheless, recall that generalized circle in the complex plane is a set of points given by the absolute value of z minus w1 by z minus w2 is equal to lambda, where lambda is a positive integer. We have seen that such a set will either turn out to be a circle or a straight line in the complex plane. So, one another way to think about the generalized circle is in the form of circles in the extended complex plane. In the extended complex plane, one could think of lines as circles with center at infinity. These are the right generalized setting which we would be considering while we study the image of such objects under Mobius transformations. So, the first proposition which I would like to prove here is the following. Let S be Mobius transformation. Then S always maps the real line with the point at infinity to a generalized circle. This is forced. Then S maps the set R union infinity to a generalized circle. Let's prove this statement. What do we want? We want to show that we want to study the set of all points W in S of R union infinity. That means S inverse of W belongs to R. We want to study all those points. In that case, let's give an expression for S inverse. Let S inverse of Z be given by AZ plus B by CZ plus D. We want to understand when S of W, S inverse of W belongs to the real line. S inverse of W belongs to R. S inverse of W will be the point at infinity precisely when it is of the type A by C. So, that I will keep aside. We will study the case when S inverse of W is in the real line. But this is if and only if from our first week's lectures this is the case, right? The conjugate is the same as the given complex number itself. So, that means i.e. notice that we are going to do an if and only if statement here, which you should keep in mind, because this is if and only if AW plus B by CW plus D is equal to A bar W bar plus B bar by C bar W bar plus D bar. Right, let's just quickly write this down in a different manner. This is just the same as AC bar minus A bar C times W plus AD bar minus B bar C times W. Oh, this is mod W square, by the way. And the second, because there is a WW bar that will come up, and then there is a term which will feature W bar, which is going to be equal to BC bar minus A bar D times W bar, and finally we will have BD bar minus B bar D. This is equal to 0. Now two cases can happen. What are the two cases? One is when AC bar is a real number. AC bar is equal to A bar C. Notice that both are conjugates. If AC bar is equal to A bar C, what will be the expression? The expression will be some alpha times W minus alpha bar times W bar is equal to B bar D minus BD bar, or rather, let me write that down in that manner because it's important to have that to the right. And this is going to be, what is going to be Z minus Z bar? That's going to be 2i times the imaginary part, right? So this is going to be 2i times the imaginary part of alpha times W. Okay, what is alpha here? Alpha is the right thing that you would have guessed. This is AD bar minus B bar C. And that is going to be equal to 2i into imaginary part of B bar D. These cancel off, and that tells us that imaginary part of alpha times W is a constant in R, which is the equation of a straight line. So when AC bar is equal to A bar C, it's mapped to a straight line. W will happen to be in the straight line given by imaginary part of alpha W is equal to C. All right, that's the case when, easier case when AC bar is equal to A bar C. So if AC bar is not equal to A bar C, then we can divide it by that number to get then if and only if, again all these cases. So here when AC bar is equal to A bar C, we are already done. We are mapping it to a generalized. Then mod W square, I'll just quickly write it in this manner: alpha W plus alpha bar W bar plus gamma is equal to 0, where alpha is just equal to AD bar minus B bar C by AC bar minus A bar C. I guess I've got the signs right, but this is precisely what alpha will be, and gamma is going to be equal to BD bar minus B bar D by AC bar minus A bar C. The expression here can be very easily rewritten as mod of W minus alpha, the whole square, is equal to gamma minus gamma will come up here. This is going to be equal to mod alpha square minus gamma. I'll leave it for you to check that this is going to be greater than 0. The conditions of the Mobius transformation will ensure that this is greater than 0, and we can look at the square root to get hold of a expression for a generalized circle, in fact a circle here. And that's going to be a very important observation because we're going to prove that with the following theorem. A Mobius transformation maps generalized circles to generalized circles. So the proof is actually quite straightforward. We pick 3 distinct points on the given generalized circle. So pick 3 distinct points A, B, C on the given generalized circle. And suppose S is a Mobius transformation. Now let's look at the image of A, B, C under S. And alpha be equal to S of A, beta be equal to S of B, and gamma be equal to S of C. We know that there exist Mobius transformations which send ABC to 0, 1 and alpha, beta, gamma also to 0, 1. Let S1 and S2 be Mobius transformations such that S1 of A is equal to 0, which is the same as S2 of alpha, S1 of B is equal to 1, which is the same as S2 of beta, and S1 of C is the point at infinity, which is the same as S3 of beta. And we have already seen that S is now forced to be equal to S2 inverse composed with S1. This is going to be a Mobius transformation, and by uniqueness this is going to be the case. The Mobius transformations coincide. Now the good thing about S1 and S2 here is that from the previous computations, S1 maps a generalized circle containing A, B, C to R union infinity. And the content of the previous proposition tells us that S2 maps R union infinity to a generalized circle. And by the previous proposition, S2 inverse maps R union infinity to a generalized circle. And we are done. So basically, a Mobius transformation always maps generalized circles to generalized circles. Okay, let me stop here.